Good evening to everyone. Welcome back to our session, day 6. In this module, we will discuss about the power factor correction converters for brushless DC motors. Before going to this session, just I want to briefly review the yesterday class. Okay, yesterday we have discussed about why we need this brushless DC motor, particularly for this electric vehicle applications, and also uh, we discussed about the basic construction details of this BLDC motor. That means actually the BLDC motor is similar to the permanent magnet synchronous motor, and also we discussed about the working principle of this BLDC motor and mathematical modeling of this BLDC motor. And the main, what is the advantage of this BLDC motor? Actually, the main advantage of the BLDC motor is that it is a electronic commutation motor. Due to this electronic commutation, we can reduce the use of the brushes. That means there is no sparking problems like DC motors. Okay. Yesterday class, I thought before going to this power factor correction converters for BLDC motor, we have to discuss about the conventional control of this BLDC motor. Okay, this diagram shows the basic conventional control scheme for this BLDC motor drive. It mainly contains the diode bridge rectifier and voltage source inverter and PWM controller and reference current generator and PI speed controller. Okay, here we can say that this entire part comes under the controlling technique for speed as well as the switching pulses of this voltage source inverter. That means indirectly speed and current control. Okay, then also we can say that using this conventional control scheme, we can control the torque as well as the speed. Okay, now here the voltage source inverter is connected to this diode bridge rectifier, and here the output of the BLDC motor is connected to this PWM controller. Okay, here encoder is nothing but the Hall effect sensors. The main use of this encoder is that for identifying the rotor position. Okay, here omega reference, that means it denotes the reference speed and omega denotes the actual speed, and theta is nothing but the position of the rotor. Okay, now the derivative part of this theta is equivalent to this actual speed of this motor. Okay, here the difference between the reference speed and actual speed is given to this PI speed controller. Okay, here the output of this PI speed controller given to this reference current generator. Okay, here the reference current generator generates these three reference currents according as per their phase currents. IA star denotes the reference current which is flowing through phase winding A. IB star denotes the phase current which flows through this phase B, and IC star represents the phase current which is flows through this phase winding C. Okay, the output of this reference current generators IA star, IB star and IC star given to this PWM controller. Okay, the PWM controller generates the switching pulses for this 2-level voltage source inverter. Yesterday we have already discussed. Here the main working mode of this voltage source inverter is 120 degrees conduction mode or two-phase conduction mode. Okay, as per the switching states of this voltage source inverter, the BLDC motor will run either in clockwise direction or anti-clockwise direction. Okay, here in this figure, the reference currents at different intervals are 0 to 60 degrees, IA star IS and IB star minus IS and IC star 0. Why? Because how can we get this table as per this? Okay, according to this switching table and these waveforms, we can generate the referred currents IA star, IB star and IC star. Okay, this table represents the rating of our BLDC motor, which is used in our simulation work. Okay, it is a 314 watt motor and these are the different parameters of this BLDC motor. Okay, here mainly we observe that it is a 4-pole motor and rated torque is 1.5 Newton meters and rated speed is 2000 RPM. Okay, this figure represents this simulation diagram of this BLDC motor. Okay, here PI controller, the what are the output of this PI controller? Reference speed and actual speed. Okay, the here error is nullified and this output of this PI controller is given to this reference current generator. Okay, here we can produce the IA star, IB star and IC star. Okay, from this we can give the pulses to this voltage source inverter. Okay, this is the simulation diagram of this BLDC motor using conventional control scheme. Here mainly we are using this voltage source inverter, and reference current generator, PI controller and PWM controller, and the supply which is given to this voltage source inverter is from this diode bridge rectifier. Okay, now if you are simulating this motor, we obtain the supply voltage and supply current. Okay, here if you are observing this figure, the voltage is 300 volts and current supply current ISA it nearly equal to the 6 amperes. Okay, but here we can say that this source current completely deviated from this source voltage shape. Okay, that means completely it will destroy its sinusoidal shape. Okay, automatically what happens? THD, total harmonic distortion level, will increase, that is 34.49%. Okay. Now, due to this disturbance of the supply voltage, what happens? Automatically, stator current, it is completely deviate from its squared shape, and back EMF, trapezial back EMF also, it has some harmonics. Okay, whenever deviations occurs in this stator current, automatically torque will be sorry. Here, if you are observing this torque waveform, okay, actually here the shape of the stator current squared, but whenever you run the PLC motor in MATLAB Simulink, we obtain this shape here, and each and every interval, if you are observing this figure, each and every interval we have some ripple. Okay, whenever change the current, automatically torque will have also some ripple. Why? Because always torque is proportional to the current. Okay, then if you are observing this speed also having some ripple. Okay, from these results we can say that whenever you are using this conventional control schemes, okay, supply current completely deviates from its sinusoidal shape, and also in motor load side current will be destroyed, and also there is some ripple in the torque. Okay, whenever the torque has ripple, the efficiency of the motor will also decrease. Okay, these are the main drawbacks of this conventional control. Okay, and another point is that here we can observe that here supply current also completely deviates from its uh, shape, sinusoidal shape. Okay, then what happens? It completely out of phase from the supply voltage. Then automatically power factor will also decrease. Okay, if you are running the motor at different speeds, okay, here at the low torque of 1 Newton meter, okay, at 1000 RPM speed, here power factor is 0.627. Okay, at 1500 speed power factor is 0.739. Okay, and it's at 1.5 Newton meters load torque. Here also we got the poor power factor 0.751. It is a very poor power factor. And also coming to the torque ripple, it also very high. How can we calculate this torque ripple from this ripple? Here torque ripple, T maximum minus T minimum T average. This is the formula for calculating this torque ripple. Okay, here from these results we can say that whenever you are using this conventional control, okay, we have poor power factor and high torque ripple. Okay, these are the main limitations of this conventional control scheme. Okay, now for overcoming this poor power factor and torque ripple, high torque ripple, okay, we are going to design different types of power factor correction converters. Actually, what is the converter? It is nothing but DC to DC converter. Okay, it converts from what is the converter? Anybody can tell? At least what is the inverter? In power electronics, mainly there are two types of converters. Converter, two topologies. Converter topologies and inverter topologies. Okay, converter converts AC to DC and inverter DC to AC. Okay, now in this today we will discuss about these power factor correction converters for BLDC motor. Okay, here mainly we will discuss about the SEPI converter which is fed to this BLDC motor and Zeta converter and bridgeless low converter. Okay, actually these main advantage of this converter is that it have high gain output voltages and also whenever you are using this type of converters we can improve the power factor. That is the main advantage. Okay, now why we go for this type of converters? Actually the basic converters are boost converter and buck converter and buck boost converter. Why we are choosing this type of converter, SEPIC, Zeta or either bridgeless Leo converter? Well, because here I think you have some idea about the buck converter and boost converter. Coming to this buck converter, it is nothing but step down converter. Boost converter is also known as step up converter. Whenever you are using buck boost, here it is also known as step up and step down converter. Okay, compared to these conventional controllers, the main advantage of this sorry, main advantage of this SEPIC, this power factor correction converter topologies are compared to our conventional converter topologies, it has high voltage gain. That is the main advantage of this proposed converters. Okay, coming to this SEPIC converter, fed to the BLDC motor. What is this full form of the SEPIC converter? Single-ended primary inductor converter. Single-ended SEPIC. Single-ended primary inductor converter. Okay, this is the full form of the single-ended primary inductor converter. Okay, here this SEPIC converter which is fed to the BLDC motor, this is the basic block diagram of this SEPIC converter fed to this BLDC motor. Okay, here if you are observing this figure, here this is the SEPIC converter. Okay, when you are observing previously in conventional controller, just replace the include this SEPIC converter along with this diode bridge rectifier. Okay, and these blocks are very common. But another thing is that in this motor side, here electronic commutation, that means that is nothing but this block represents the PWM controller. Okay, here okay, this entire marked area is for switching the pulses to this SEPIC converter. Okay, here actually these special type of converters like power factor corrector converters, SEPIC converter or Zeta converter or BLLC brushless Leo converter, there are two types of patterns for giving these pulses. First one is the voltage multiplier techniques and another one is the current multiplier techniques. Okay, here mainly in our work we are using this voltage multiplier technique. Here this block represents the reference voltage generator. It can be generated from this reference speed omega star, and it also the speed is converted into the reference voltage VDC star. And here the difference between the reference voltage VDC and the output of this VDC SEPIC converter is given to this voltage controller VE. Okay, here the voltage is given to this PWM generator. Okay, and here the sawtooth generator produces the modulation signal MD. Okay, here the PWM generator generates the pulses to this switch SA. Okay, here if you are observing this figure in the SEPIC converter, mainly two inductors L1 and L2 and two capacitors C1 and CD and one switch SA and one diode D. The charging and discharging rate of these inductors and capacitors, we will get the output voltage. That means we can either step up or step down this output of this SEPI converter. Now, here this figure shows the various working modes of this SEPI converter. Okay, here actually three modes of operations. This is the mode A, mode B and mode C. In mode A operation, switch SA is in on state. Whenever SA is in on state, the current IL1 flows through this L1 and the current IL2 flows through this IL2. Then C1 starts to charge. In this instant, the diode D will be in reverse biased. Okay. From this, if you are observing this waveforms, here whenever SA is on, IL1 has increasing and IL2 has some value up to SA1 is off and VC1 has changed and VDC also has changed. Okay, now coming to the mode B. Okay, that means if switch SA is in off state, the voltage across this VC1 gets discharged. Okay, here again there is a change in voltage across this C1 and also voltage across the CD. Okay, from mode P. Now, here in this mode, still SA is in off state and gets ready to off. In this state, delta IL1 represents this change in inductor voltage, that is nothing but delta IL1, and change in capacitor voltage VC1, that is represented by delta VC1, and change in this DC link voltage VDC, delta VDC. In this way, for every instant of time, based on this switching states of this SA, the voltages across the capacitors and currents in inductors will be changed. This is the basic operation of SEPI converter. Okay, here now if you are running this SEPI converter in a MATLAB program, we have obtained this supply current. Okay, in previously in conventional control, it completely detroits its shape from this sinusoidal waveform. But here, whenever you are using this SEPI converter, here the shape will be sinusoidal wave. Okay, in previously THD is 34, approximately 34.1%. in conventional control. But in this power factor corrected CP converter, we got the THD 2.69%. Why? Because this shape of the supply current is, it's nearer to the, almost nearer to the sinusoidal. Okay. Now, okay, these are the stator phase A current, and this is the trapezoidal back EMF waveform, and figure C represents the speed, and this is the waveform of the torque. Okay, here if you are observing that it is also, it is very nearer to this squared waveform. Okay, then automatically the torque ripple will also decrease. Okay, these results represent whenever the motor runs at 1000 RPM. Okay, in the in this case, if you are running the motor at 2000 RPM, again the shape of the stator current is also nearer to this square wave. Okay, automatically the ripple factor in torque will also decreases. Okay, if you are observing this results compared to conventional controllers, we will obtain improved power factor and also less torque ripple. Okay, this is the about CP converter which is fed to the BLDC motor. Okay, now another converter type is zeta converter which is fed to the BLDC motor. I think you will get one doubt, sir. Actually, here also you are improving the power factor. Okay, what is the difference between zeta converter and CP converter? Why you go for this zeta converter? Anybody can tell? Here also, if you are observing this zeta converter, here also we are using one switch and two capacitors, two inductors and two capacitors and one diode. Okay, here switch is connected in series with this supply. In previously, this switch will be connected across this. Okay, and this inductor, the placing of the inductor and capacitors are interchanged. Why? What is the difference between this zeta converter and CP converter? Anyone? Okay, I will explain. Once again, come back to this CP converter. Okay, here if you are observing this figure, here also same components. Switch one we are using, it contains one switch, two inductors and two capacitor components. In Zeta converter also having one switch and two inductors and two capacitors. Why we go for this Zeta converter? Because of compared to SEPI converter, Zeta converter has high efficiency. But in general, I am talking about whenever you are using the application only for electric vehicle applications, particularly when you are using the BLDC motor only. Actually, in general, theoretically, compared to SEPI converter, Zeta converter has more efficiency. But in this case, you have to remember that particularly whenever you are connected to this BLDC motor, compared to SEPI converter, Zeta converter has less efficiency. Just it is also working. It can also improving the power factor. But compared to that SEPI, Zeta converter has less efficiency. Why? Because in later we will discuss. Okay, first we go through this Zeta converter. Okay, this is the block diagram of this Zeta converter. Here also same. It is the diode bridge rectifier and it represents the DC filter, and simply SEPI converter is replaced with this Zeta converter, and this is it is connected to this voltage source inverter. Okay, here also we are using the same technique, voltage multiplier technique. Okay, here the reference speed is given to this reference voltage generator, and the reference voltage VDC star, the difference between this VDC star and VDC is given to this voltage controller. Okay, the output of this voltage V and sawtooth generator modulation X MD given to this PWM generator. Based on the signals, PWM generator generates the pulses and operating this switch SZ. Okay, here now coming to the different types of working modes of this Zeta converter. Here okay, here also mode A, mode B and mode C. Okay, first in mode A, that means if SZ is in on state, what happens? Whenever it is in on state, the current IL1 flows through this L1 and IL2 current flows through this L2 and VC1. That means voltage across this C1 will be changed. Here C1 will get to recharge, charging, start this charging. Okay, here if you are observing this waveforms, here IL1 from changing 0 to some value and IL2 will also change, and due to the reverse biasing of the diode D, at the instant of SZ on, it will be 0 and the voltage across the C1 will be changing from some reference value to another value, and VDC will also change. Okay, coming to the mode B, here SZ will be off. Okay, if you are observing these waveforms, here IL1 will be decreased from some value to this 0. But actually it is not completely goes to the 0. Okay, here IL2 also from changing from one value to the some value. Okay, and what about VC1? It will also start to decrease, and the voltage across the VC1 also changed. Okay, here mode C. Here also whenever SZ will be off, the diode D comes to the conduction. That means it is the forward biased, and the current through this ID will be changed. Okay, now in mode C, here SZ starts to again still it is off state at the instant while off state of this SZ, T comes to the reverse biased. That means again VC1 gets discharged, start to discharge, and the L2 starts to charging. Okay, now if you are observing this, the different currents in L1, L2, and voltage variations across these capacitors VC1 and VDC, at every instant of time it will be varying. Okay, these are the different types of working modes of this theta converter. Okay, now if you are running this theta converter in MATLAB Simulink, here we obtain the supply current like this. Okay, here it is almost nearer to this sinusoidal shape, and here the THD value is 2.12. Okay, from this we can say that compared to SEPI converter, theta converter get less THD in supply current. That means supply side. Okay, now if you are observing stator phase current, stator current, and back EMF waveforms, here IR represents the stator phase current for phase A, and EA represents the back EMF waveform in a phase A. Okay, now here also almost we obtain the sinusoidal waveform, sorry, square waveform. Okay, here automatically we get the less torque ripple. Okay, these results shows the for running the motor at 1000 RPM. Okay, here again here also whenever the motor runs at the rated speed of 2000 RPM and rated torque 1.5 Newton meters. In this case also, we obtain the improved stator current waveforms and back EMF waveforms, and also have less torque ripple. Okay, from this discussion we can say that compared to SEPI converter, Zeta converter has can give the improved results. Okay, now going to the another power factor corrected converter topology. Bridgeless Leo converter fed to PLC motor. Okay, up to now we have discussed about Zeta converter and SEPI converter. Now, what is the use of this bridgeless Leo converter fed to PLC motor? Anybody can tell? Okay, actually, we know there are mainly two types of converters. Basic, apart from that boost, whatever the type of converters, uh, we have two types of converters. What is that? Isolated converters and non-isolated converters. Okay, here the main advantage of this type of bridgeless isolated converters and non-isolated converters, we don't require any extra components like transformers. Okay, and this type of bridgeless low converter coming under the category of this isolated converter. Okay, here mainly we don't need to use any bridges. Okay, here main components of this bridgeless low converter is two switches SW1 and SW2 and two inductor components Li1 and Li2 and L02 and L01 and L02 and C1, C2 and two capacitors. Okay, here also we are using the voltage multiplication technique for giving this pulses to this switches SW1 and SW. In previous converter topologies, either Zeta or converter, we are using only one switch. But in the case of bridgeless Leo converter, it consists of two switches SW1 and SW2. Okay, here also again reference speed is given to this reference voltage generator. Okay, the output of the reference voltage VDC star and the actual voltage VDC. Okay, the difference between the VDC star and actual voltage of the VDC is given to this voltage controller, and the inputs of this voltage controller V and sawtooth generator MD is given to this PWM generator. Here the PWM generator generates the switching pulses for SW1 and SW2. As per this switching pulses SW1 and SW2, it will be operate. Okay. Now, if you are running this BLL converter to this in the MATLAB, okay, again we obtain the supply current which is nearer to this sinusoidal shape, and THD also very less, 1.79. In previous converters, I think it maximum for SEPIC 4%, and next Zeta converter 2.2 something, and for this bridgeless converter 1.79%. Okay, and when the motor is running at 1000 RPM speed, here also the stator current are also, it is very close to this square shape. Automatically the ripple of the torque will also reduced. Okay, and if you are running this motor at the speed of 2000 RPM, here also we obtain less torque ripple. Okay, now if you are summarizing all three types of converter topologies in a tabular form, okay, here at the load torque of 1 Newton meter at 1000 RPM speed, with conventional controller we obtain 0.627 supply power factor. Okay, with SEPIC configuration it is 0.956, and also whenever you are using the Zeta converter it is 0.97. Okay, whenever you are using this BLLC configuration, that is nothing but brushless Leo converter topology, we obtain 0.987. Okay, this, if you are observing at constant torque and various speeds like 1000 RPM, 1500 RPM and 2000 RPM, at each and every case we obtain the improved power factor compared to this conventional scheme. Okay, and in another case at the load torque of 1.5 Newton meter torque, here also at 1000 RPM we obtained improved power factor, that is 0.965. With Zeta converter configuration it is 0.973, and BLLC we obtained 0.987. Okay, here also at various speeds with a constant load torque of 1.5, here also we obtained improved power factor. It is approximately equal to 1.988. Okay, and here converter to converter topology, always it is increasing order. Okay, coming to this torque ripple, here also when you are using conventional control scheme at this load torque of 1 Newton meter and at 1000 RPM speed it is 21.89%. At 1500 speed it is 36.8, At 2000 RPM speed, it is 40.32. Now, coming to this proposed converters, at each and every converter topology, it will be reduced. Here, 29.13, 28.1. Here, 38.31. In the with the SafePick configuration and with JETA configuration, it is 36.81, and with BLLC configuration 35.8. Okay. Now, at the instant of 1.5 load torque, it is also 32.9, 32.4, 29.8 and 25.7. And at rated speed of 2000 RPM and rated torque of 1.5, it is 43, 40.2 and 36.48. Okay, from this table, what are the main observation? Anybody can tell? Here, power factor will be improved. But coming to this torque ripple, compared to conventional control configurations, it is less. But we have to reduce the torque ripple. That is the main challenging task. Okay. From this, we can say that whenever you are using power factor corrected converter topologies which are fed to this BLDC motors, even though supply power factor is improving, torque ripple is the problem. Okay. For this, what is the solution for this? Now, we will take a small break. After the break, we will continue. How can we improve the power factor as well as the reducing the torque ripple? Okay. Take a short break. After 10 minutes, we will back. Okay. Welcome back to session. Okay. Now, up to now, we have discussed about different types of power factor converter topologies. Okay. Here, SEPIC, JETA configuration and PLLC configurations. Okay. Here, we are connecting these power factor converter topologies to this our brushless DC motor. Here, from these results, we can observe that only supply power factor has improved. But if you are observing torque ripple, okay, there is much more improvement. Even though we are using this type of power factor correction converter topologies like say PIC, JETA or BLLC. Okay, now you will get one doubt, sir. Now, what is the use of this power factor converter topologies? Okay, is there any method for improving both power factor and reducing this torque ripple? Okay, I can say that yes, there are so many methods. Okay, now we are going to discuss modified power factor corrected based converters with torque ripple minimization. Okay, up to now we are using this power factor corrected converters for improving the power factor. Okay, whenever you are using this modified PFC based converters, we can reduce the torque ripple along with the improved power factor. Now, first of all, how can we modify this power factor converters? Okay, which method we are using now? We'll discuss. Okay, in this torque ripple minimization, actually we have already discussed about this equivalent circuit. Okay, here for example, this is the pure ideal stator current. Okay, let us say it will be phase A current IA. Okay, now in previous case we are using okay. Let us considering this stator current. Okay, here when you are observing this stator current of phase A, here there is some dip. That means here there is a change in current delta I. In this case, it will be decreased, and also voltage also in back EMF waveform will be decreased. Okay, at this time of instant it will be decreased, and at this time of instant it will be increased, and at this time of instant it will be decreased. Okay, according to increasing and decreasing of voltages and currents, okay, always at the time instance, whatever it may be, either increasing or decreasing, according to this increasing or decreasing, we have to insert this decreasing voltage or reducing the increased voltage based on the instant. Okay, for this okay we have already known these equations. Dia by dt equal to minus 2 by 3L VDC plus 2 by 3L into E. Okay, and this is for the phase current IB, and this is for the DIC by dt equal to 1 by 3L VDC plus 2 by 3L E. Okay, here the main concept of this method is that we are injecting the voltage wherever it will be decreased. Okay, that additional voltage will be equal to this VDC to 2, that is equal to 2E into E plus 3R I naught by 2 minus VDC 1 by 2 plus K into T commutation by 4. Here E represents the back EMF. We now already know that R represents the resistance of this phase winding, and I naught represents the phase current, and VDC 1 is the DC input voltage, and T com represents the time of the computation period, and K is the constant. According to this equation, always at the instant of time, we have to injecting this additional voltage wherever it required. This is the one of the method for decreasing the torque ripple. Okay, now coming to this modified SEPIC converter. Here we have already discussed. This is the side bridge rectifier, and this is the DC filter, and this is the modified SEPIC converter. Okay, here always these are the additional voltage sources. Okay, these additional voltage sources will be connected across these three winding. Okay, phase A, phase B, phase C, these are connected to each leg of this voltage source inverter. Okay, and here using this voltage multiplier technique, we are given the switching pulses to this modified SEPIC converters. Okay, here whenever you are connecting these additional voltage sources, okay, now if you are running this modified SEPIC converter, okay, these are the simulation results whenever the motor running at 1000 RPM speed. Here this is the supply current. Okay, here if you are observing the THD of the supply current, it is equal to 2.69%. And now VAB represents the converter output voltage before adding this additional voltage. Okay, here this is the VAB converter output voltage, SEPIC converter output voltage. Okay, now if you are adding this extra voltage using this extra voltage sources, here there is one additional voltage spike. Okay, now after adding this additional voltage, if you are observing this diagrams, here the stator phase current A, it is almost nearer to this squared waveform. That means it is trying to reach this squared waveform. Okay, here whenever you are injecting this additional voltage at this instant of time, the ripple of the current will be decreased. Then automatically the ripple in the torque will also decreased. Okay, here at each and instant of time, okay, at each and every instant of time, that is in this case we are considering always there is some dip in the stator phase current. Okay, according to this decreasing voltage, we are injecting that additional voltage. Then the shape of this stator current tries to reach the ideal shape of square wave. Then automatically torque ripple will be reduced. This is the concept of the additional voltage injecting in converter output voltage for reducing this torque ripple. Okay, the main advantage of this type of modified converter topology is using these additional voltage controllers. Here, along with the power factor improvement, we can also reduce this torque ripple. This is the main advantage of this modified converter topologies. Okay, these results for the modified SEPIC converter now. Okay, here and also in previous slide the motor is running at 1000 rpm. Okay, in this instant the motor is running at 2000 rpm. Okay, here also there is some dip. Okay, here compared to uh, PFC converters, the shape of this stator current will be improved. Okay, it is also nearer to this square waveform. Okay, and another thing, if you are observing the speed also, here we have obtained the smooth response compared to previous ones. And also whenever decreasing the ripple in the stator current, automatically the ripple in torque will also decreasing. Okay, in chart box one of the student asked me how can we calculate the torque ripple. Okay, previously I have already discussed, once again I will explain. For calculating the torque ripple there is one formula, T torque ripple equal to T maximum minus T minimum divided by T average. Okay, here T maximum means if you are considering this spot. Okay, here this is the 1.5 something, this is 1.8. This can be taken as 1.8 as the T maximum and upper ripple is considering as T minimum. And also, you know already T average equal to T maximum plus T minimum divided by 2. Okay, from this formula, we can calculate the T average. From the T maximum minus T minimum divided by T average, we will get the torque ripple value. Okay, got it? Here, just injecting the additional voltage, okay, as per decreasing value, we can reducing the ripple in the current. Automatically, we will get reduced torque ripple also. Why? Because torque is always proportional to I. Okay. Sorry. Now, in previous case, we discussed about the modified CPIC converter. Okay. Now, in this case study, we discussed about the modified bridgeless low converter fed to PLDC motor. Here also, again, we are keeping this additional voltage source to this each leg of this converter, and these additional voltage sources connected in between this voltage source inverter and this PLDC motor. Okay, here also same. Here also we are using the same voltage multiplier technique for giving the pulses for SW1 and SW2 switch. These are the SW1, SW2 switches. Okay, here another important thing you have to remember that in previous case also, compared to CPIC and Zeta converters, bridgeless low converter has given uh, best results. Okay, in this case also, okay, whenever you are using this additional voltage source method, in this case also it will give the best results compared to other converter topologies. Okay, now whenever you are running the motor in a MATLAB Simulink, here the fundamental component of the supply current is 1.67. Okay, that means here we obtain the total harmonic value THD is very less. From this we can say that here automatically power factor will be improved. Now here also same. If you are observing this figure, okay, this one is the decreased voltage. Okay, now if you are adding or injecting this extra voltage, automatically VAB will be increased. VAB is nothing but the line voltage of this converter. Now if you are running the motor at 1000 RPM. Here also the shape of the stator current. You can observe this here. It is also nearer to the squared waveform. Okay. Whenever improvement in the stator current, the ripple factor is also decreased. Okay. And the speed of the motor is also smoothens. Okay. In this case, also torque ripple is less compared to previous PFC BLLC converter. Okay. This in this, whenever the motor running at 1000 RPM, here also after injecting the additional voltage through this additional voltage sources, the stator current ripple will be decreased. At the same time, the torque ripple will also decreased. Okay. Is there any doubts? Okay. Now, these are the different schemes for different methodologies. Okay. Now, coming to this supply power factor. Here, when the motor is running at 1000 RPM, in conventional scheme, we obtained 0.751 power factor, and bridgeless Leo converter for BLDC motor is 0.985, and this proposed method, it will be 0.981. And also it is almost equal. Okay, when the motor is running at 2000 RPM, here in conventional scheme we obtained 0.753, and whenever you are using PFC converter, it is 0.99, and proposed scheme, it is 0.99. Okay, coming to the torque ripple, when the motor is running at 1000 RPM, in the case of conventional scheme, we obtain 37.8 torque ripple, and BLLC fed BLDC motor, it is 28.9. Here, this converter is only power factor converter. After modifying this BLLC with an additional voltage source, we obtain the torque ripple 13.6, which is very less compared to this BLLC and conventional scheme. And when the motor is running at 2000 RPM, conventional scheme has 48.27 torque ripple. In BLLC fed BLDC motor, it is 36.48. Whenever you are using this proposed scheme, it will be 16.43. Okay, from this we can say that apart from the power factor converter topologies and conventional schemes, using this type of modified converters like modified SEPI converter or modified Zeta converter or modified brushless Leo converter, bridgeless Leo converter, we can improve the power factor along with the reduced torque ripple. Okay, is it clear? Okay, this is all about the different types of converter topologies for power factor correction as well as the torque ripple minimization. Okay. Now, if you have any doubts, please type in chat box. Okay. I think no one has no doubts. Okay. In this class, various types of converter topologies, Zeta converter, SEPIC converter and PLLC converter, Zeta, SEPIC and bridgeless Leo converter, and also along with this PFC converter topologies, we are discussing modified converter topologies. Like modified SEPIC, modified BLLC topologies. Okay, the main advantage of this modified converter topologies, we can reduce the torque ripple along with the improved power factor. Okay, I hope this class will useful to gain the knowledge on various types of power factor converters and modified power factor converters. Okay, thank you. We will meet on the next session. Thank you.